Roger is a senior principal consultant now with the company called Inspection Experts after recently retired from the Savannah River National Lab with more than 33 years of experience in waste management. He currently provides technical and policy support to DOE, the IEA, and to multiple DOE sites on performance assessment and waste management related activities. His career has included support for activities related to disposal, remediation, and facility decommissioning and closure across the United States and in more than 15 different countries. He has also contributed to peer reviews and or recommendations for various organizations including IEA, DOE, NRC, EPA, National Academy of Sciences, and the National Council on Radiation Protection and Management. Roger is going to talk to us today about his work to document the philosophies and ideas that he has accumulated over the years through his work on how to manage uncertainties as part of the steering committee's supported activities.
Thank you, Ming. And this topic of managing uncertainties is something that I really started to dive into about 10 years ago, and I was leading a working group at the IAEA where the topic came up as something that we needed to do a little more work on. And one thing that became very clear pretty quickly is it's not new. It wasn't new at that time. There have been a lot of discussions of uncertainties and how we manage them. And in fact, Steve Golian gave me a copy of a white paper that he wrote 25 or 30 years ago talking about uncertainty management. So this, I think what we've done is tried to collect information and communicate the information. But one thing I challenge you to do through the presentation is think about all the things that we are really doing, how much of that is directed at managing uncertainty. So as Ming mentioned, this is kind of an advertisement for a draft white paper that was prepared, and it's with the steering committee now. The white paper was completed in April. It's an overview. It's not intended to be an in-depth study, but it's kind of teasing your interest and giving ideas of all the different approaches that are available to manage uncertainties. And it addresses disposal. It started as a disposal task at the IAEA, but it's been expanded to include considerations related to remediation and closure as well. Performance and risk assessment. So I think we're all here. We all recognize that there's a lot of uncertainty associated with any types of projection of behavior far in the future for natural or engineered systems. So uncertainty is an inherent fact in what we have to work with to make decisions. One thing that we've kind of expanded when we had the IAEA working group was the idea that we've got these kind of three typical areas. We have programmatic uncertainties, technical uncertainties, and contextual uncertainties, and I'll talk a little bit about each of these. But we also added in a couple more related to resources and things based on when the IAEA was looking at it, you've got a wide variety of conditions in different countries. One thing I like for people to think about, we talk about reducing uncertainties. As you're thinking through different uncertainties, think how many of them truly are reducible and how many of them are things we don't have control over. We can't really reduce them. So our first reaction tends to be, okay, what can we do to reduce uncertainty? And I think this goes back to the RAGS document, which is 30 years ago. And even at that time, there's a quote in there that complete characterization of a site during the RIFS in the sense of eliminating uncertainty is not feasible, cost-effective, or necessary for the selection of a suitable remediation action. So we want to do the best we can to manage uncertainties, but we shouldn't set unrealistic goals that we're going to completely remove uncertainty. And so that leads to this idea that what we're really seeking to do is manage uncertainties. And I'll talk about how part of management is identifying and prioritizing those uncertainties, kind of along the lines of what Mike talked about this morning, the importance of prioritization. And the prioritization is focused on what's significant for the decision that we're trying to make. So this actually started from some work that was done for high-level geologic disposal internationally, and they had kind of these 4 steps for uncertainty management. So this is based on that, but it's been changed based on the discussions that we've had over the last decade or so. The first step is awareness. You're not going to manage uncertainties if you're not first identifying them and clearly acknowledging that the uncertainties exist. Then we talk about importance. So once we've identified the uncertainties, how do we determine which ones really matter? Where should we be focusing our attention? And then you can move into the area, okay, how are we going to reduce these uncertainties? How are we going to manage these uncertainties? And one of the emphases of this task was identifying a wide variety of options that we do use to manage uncertainties. And finally, then, it's quantification, communication. Not always quantification, I guess, but always communication. The important part is communicating how we have managed these uncertainties such that we can make a good decision. We can make a defensible decision. I'm going to skip the awareness first. I'll come back to that, but I thought I'd start with importance just to keep us focused on an important part of this process is really identifying where we should focus our efforts. And this is a document from about 10 years ago that the EPA produced on environmental models, basically, and their use for decision making. And in that document, they place a lot of emphasis on this. We need to identify those uncertainties that matter. We need to prioritize our efforts on those things that are important for the decision. Because I think we all know, there's any number of uncertainties that would be associated with what we do. In order to get to a decision, we really need to focus on those that matter. So back to awareness. First step in awareness, what types of uncertainties are there? We've got the traditional data and parameter uncertainty, just variability over space. There's going to be changes over time as well, so you may have variability over time, and there's just basic lack of knowledge about some of these parameters in the environment. Then we have modeling uncertainties, just our conceptual models, our mathematical representations. They're approximations of what is specifically happening in the environment. And those models may change over time as well, and there's uncertainty in how things change over time. Then some of these are reducible. We talk about data and parameter, although variability is not reducible. But some of these uncertainties, by spending more time on models, collecting additional data, you can help reduce some of the uncertainty. But when we think about future and scenario types of uncertainties, what is our member of the public going to eat 1,000 years from now? We should not imply that we know what they're going to eat 1,000 years from now. So what can we do to manage that uncertainty? What we typically do is assume there's some reference set of conditions that would be protective now, and by doing that, we're assuming we're protective in the future. The 2 areas that we added in the IAEA project are just fundamental resources. Do you have the resources available to manage the uncertainties? Financial, human resources, technologies. And contextual types of uncertainties, these are things like regulations. We know regulations can change over time. Stakeholder opinion. Why are we engaging with the stakeholders? It's better for us to know at the beginning what's important to them, what matters to them, than to wait till the end and throw them this document and say, you agree, right? So we're managing that uncertainty with stakeholders by engaging them throughout the process. Regulations, regulations are changing. There's Part 61 is being revised now. How do you manage that kind of uncertainty? ICRP changes their dose coefficients over some semi-regular time. How do we manage that? If it was protective in 1990, the coefficient changes. Is it still protective now or not protective? So these are these contextual uncertainties that can be really hard to address. So now a variety of different sources of uncertainty. In the document, there's some examples over different time frames over the life cycle of an action. This is an example box from the time frame for closure and active institutional controls. These are just some examples. I'm sure all of you could think of more, but just a few things. Do we have the resources to maintain institutional controls? Have we allocated resources to continue monitoring that we've committed to do? Will the performance of the facility or the remediated site be consistent with the assumptions that have been made in the model? And that's, Rob talked about the 5-year reviews. That's one of the questions that they're working with. A simple question, we talked about this at lunch, in fact. When we're designing these covers, did they actually think about where they're going to get the material to build a cover that's a certain thickness? And that's been a challenge in the complex. Originally, there were these grand designs for very elaborate covers, and now people are realizing that very elaborate covers require a lot of material, and they're very expensive. Quality assurance, that came up this morning, and in Dave's presentation. Can we actually implement what we said we were going to implement? And just the regulatory requirements, and that touches on what I said before. How do we manage potential changes in the future? As I mentioned, one of the main points of the document is this idea that there's many different ways to manage uncertainties. So this is kind of a partial list of some of them that are described in the document. They're actually broken into 2 categories, and there's a lot of overlap, but one category we talk about confidence building, things you can do to build confidence in what you've done. And the other category is approaches to manage uncertainty. So there's 2 different tacks that are taken in the document. And the document includes a few references, but there's no intent to try to be comprehensive. It's more to get people thinking that there are a lot of different things that we do to manage uncertainties. I'll touch on a couple examples from this list, but I'll just things like sensitivity uncertainty analysis. We use that to address some uncertainties. You can do additional characterization. We use expert elicitation in some cases. Plume matching, if you have an existing plume at a site. You can do demonstration projects to run in parallel with an action to look at how things change with time in a controlled situation. Monitoring and surveillance are very popular as well. So any number, and I think when you think about it, we're actually doing a lot of what we do, as I mentioned before, is oriented towards managing uncertainty. So we do a lot of these things just as a matter of course. So one that I'll touch on, the first thing, when we develop our regulatory requirements, there's safety factors built into those requirements. And sometimes we lose sight of that our target, our end target for compliance already has some safety factors built in. So typically when we're looking at and this is focused on dose, you could make similar arguments for risk as well. Our requirement for disposal is 0.25 millisievert, 25 millirem per year. EPA radiation requirement is 0.15 millisievert. There's guidance now that says 0.12 or 12 millirem. Air pathway is 10 millirem, 0.1 millisievert. Drinking water is 4 millirem. So we're talking ranges a few millirem. If we compare that to a transcontinental flight is roughly 5, round trip is about 5 millirem. So we're in the range of, one of the guys from Energy Solutions says, we're in the range of silver medallion on Delta when we're talking about these levels of dose. So how does that compare to other things? 1 millisievert, 100 millirem is the absolute limit for all sources. And that's based on a linear extrapolation from observed doses at much higher levels. If we look at the background, the average annual dose from all sources in the United States is 620 millirem. And that includes medical procedures. So it's been bumped up more recently to reflect the medical procedures. So granted, that's biased towards some of us that are a bit older that are going through some of these procedures. One thing that I'll focus on is radon action level, and Mark mentioned his basement measurement. But if you use the EPA dose calculator, and I've got a site for that, and calculate the dose for 4 picocuries per liter, which is the kind of mandatory action level, that's about 580 millirem per year. So Mark, I'm sad to report, but you're over 1.5 rem. So not saying we should change requirements, but just recognize that we're getting much higher doses from all kinds of other exposures than what we're regulating to in this case. And if you look at worker standards and even the actual dose leading to fatal cancer, you get to some much higher levels as well. Just another perspective on this, where you live. When you look at differences in your dose depending on where you live, it's on this order of what we use for our regulations. The difference between, I'm not sure if you can read this very well, but we're on the Atlantic coast now. It's about 23 millirem. If you're going back to Colorado or New Mexico, you're jumping up to 90 millirem just based on where you live for the terrestrial dose. Also, elevation. The elevation you live at affects your dose. And if you're Colorado Plateau, the cosmic radiation is about 21 to 29 millirem per year. So all these numbers are in the range of what we're regulating to, which would equate to just based on where you live. Another aspect that came up, and I think several people this morning talked about monitoring and the role of monitoring in this. So one thing that is a very important way of managing uncertainty is actual monitoring of the environment. In the Department of Energy technical standard, and this is also, you'll see this in IAEA documents as well, there's this concept of compliance monitoring or performance monitoring. Sometimes people will call it functional monitoring. And you need both, really, to really support the effectiveness of our decisions. We can't just be focused on compliance. We need things that give us a little more indication. So what do I mean by compliance and performance? Compliance monitoring, you're measuring, say, a concentration in an aquifer or in air, and comparing it to a regulatory standard. Either you comply or you don't comply. And I think that's the way, and my sense is the public is reacting to monitoring based on that kind of monitoring. If you get a number above the number you're supposed to get, there's a problem. Performance monitoring isn't that absolute. I would say performance monitoring is something where you're not directly comparing a concentration to a regulatory standard. There's some interpretation involved. You're measuring some property that's indicative of how effective your solution is, but it's not directly comparable to a standard. It may be compared to a model result. It may be compared to an assumed value that was used in your modeling. One thing we have to be careful of with that kind of monitoring, we need to do it, we want to do it to help to build confidence, but it can quickly increase uncertainty if you don't carefully communicate what you're trying to gain from that monitoring, the purpose of the monitoring, and the range of results, the range of conditions you could see. One thing, like with sensors, there's a lot of work on sensors now. How reliable are the sensors? You need to be very careful about that, because when you're presenting things and you're making promises to the public that we're doing this monitoring to show that it's safe, and then, okay, what do you do when you get a measurement that's outside what you were expecting? And I'll talk a little bit more about that on the next slide. Another figure, this is a figure I've used for quite a while now. It's just emphasizing ranges of results. So if we run a model, we get some concentration versus time. That's the black line. So if you run a deterministic model, here's what our model says it's going to be. Then you start taking samples, and sure enough, one of your samples is above that line. Major problem. If you've done it recognizing ranges, if you've communicated that we're expecting ranges, not just one single number as a function of time, if you've run a probabilistic analysis or you've communicated ranges, that 1x above your deterministic line just becomes another number well within the range of expected results. So just a few things. So if we start thinking about performance monitoring, looking at these indicators rather than absolute concentrations in air or an aquifer compared to an MCL, for example, if we're looking at other things, some things we need to keep in mind. Modeling, what we're trying to do is demonstrate that things are going to be acceptable. Generally, we're going to be within the acceptable range. Our remediation is going to lead to a situation that is within regulatory standards. We're not trying to say that our model is an exact prediction of what's going to happen. I think you're setting yourself up for failure if you're comparing your monitoring program with this intent that it is exactly what's going to happen. Sometimes these things may not happen right away. If you have a heavily engineered system, what are you going to monitor? Because you really won't expect to see a lot of things happening over time. So how do we get things closer to the source and get reasonably representative information? A lot of times we do things in the vadose zone, for example, rather than wait until it gets to the aquifer. Heterogeneity is a measurement in one location indicative of what's happening for the average system. And I think Mark made an interesting comment. We're intelligent about, I shouldn't say always, but I think we really try in monitoring to focus where we think there's going to be a problem. So there can be bias there. We're going to have more monitoring where there may be a problem. Is that indicative of a failure of the whole system, or is it indicative of knowing where we would expect to see things happening? Is it a trend, or so we've got spatial variability, but temporal variability as well. Is it a trend or a one-time measurement? We should be more concerned about trends. But you can't ignore, when you get that one measurement, you need to start to drill down and try and understand why. And of course, we don't want to install instruments that are going to change the properties of the system, which can be a challenge if you really want to get information in the vadose zone or something. How many penetrations do you want to make to try and get that information? So just some cautionary things. I think we know monitoring is important. We know that we need to do it, but just be careful when you do it, that you're communicating well why you're doing the monitoring, and you communicate well the expectations for values. For performance monitoring, it shouldn't be an immediate alarm for the public if you see some numbers that are a little bit above or outside the range you expected. And you need to, it's much easier to communicate that before than to try and explain it after you get that measurement. There's a good example in Spain. They use vaults for disposal. And what they did, they created a double wall system basically. And they had promised the public that this double wall system is going to illustrate how we will never see water. There's no water getting into the vault. Sure enough, a few years later, there was water in between those two walls. Then public concern, they told us it wouldn't be, now there is. But when they peeled it back, they realized, okay, these vaults were exposed to the environment. They're exposed to temperature changes. The wall would heat up on the outside, cool down, heat up, cool down. Condensation formed inside between the walls. The condensation was collecting in there, just from the humidity in the air in that gap. So, yeah, the cautionary tale is be sure to think very carefully about the purpose of the monitoring and what you could expect to see depending on the type of instruments that you're using and the parameters you're measuring. So just to wrap it up, there is this white paper on managing uncertainties. It's with the steering committee now for review, and I imagine it'll go to the whole group at some point here. It addresses performance and risk assessment, so we talk about things relative to remediation and closure and disposal. As I mentioned, one of the key points is there's many different things that we do to manage uncertainties, and actually we've been doing them for years. And we just may not always capture that this is what we're really trying to do. The standards that we use already have these safety factors built in, And I think that's just something to keep in mind when you're interpreting the results of modeling. From my perspective, it's something to really, that's probably the time when it's most important, because typically we want to test our models. You're going to ask all kinds of what-if questions. So we're going to run cases. What if this barrier is not there? What if it fails? You may get a bigger number in that case. And just keep those numbers in perspective. And finally, monitoring, you need to communicate very carefully, especially for performance monitoring, where there's interpretation involved and there may be new technologies, different kinds of sensors. Carefully communicate the purpose and expectations for performance monitoring especially. And that's